We've done A, B, C, D. Okay, so I don't have A, B, C left anymore. I deleted that page because I need room for my algebra 2 pages. But, so A, we use the difference quotient to find the slope of the curve at x equals 9. So we used our definition of a limit. B, we wrote the equation for the linear approximation. Okay. C, we use that equation to find that value in C. D, we graph the function and its tangent line at x equals 9. And now we're ready for E. Explain whether your answer to C is an overestimate or underestimate for the actual value of square root of 9.1. Justify your answer by reference to the behavior of the graph of f of x equals the square root of x. Huh?
Overestimate.
Why?
Because our tangent line is above.
Right? Okay. So the idea here that value on C, okay, that value on C came from the equation of linear approximation, aka the tangent line. And so our tangent line here, our tangent line is above the graph here, yes? So like right here, this point here is 9, 3. Well, hard to write it, you know, I can't write it close enough, but this point here is going to be the 9.1, comma, what did I have? 3.0166. Because that is on the tangent line, and that tangent line is above, it is an overestimation. So what I have written down here for mine, f of x, it's concave down, okay, because we talked about concavity, right? That purple graph is curving downward. F of x is concave down. Estimate is an over approximation because the tangent line lies above the curve. Hello? I don't think so. Okay. Yeah, I can double check. I'm going to work on membership later, and I can double check, but I don't think so. Lindsay Sorensen should be asking you for a new withdrawal paper. Okay, good deal. I'll explain that situation later, but yeah. So okay, bye. Okay, did you write something?
What is the rest of it after it concaves down?
So f of x is concave down. And what did I say next? So estimate is an over approximation, or in other words, overestimate, if you prefer to stick with that word. Since the tangent line lies above the curve. The tangent line lies above the curve, or in other words, above the function. If you haven't already done F, do F. I got it started. Square root of 9.1 is 3 point something.
0.16620.626.
Can we just do 3.0166?
No,
No,
because
we got,
that's what we got in part C.
Oh.
Okay. So here we need to go, so 3.0166.
2 0
Okay.
6.
2,
2
6.
6.
Oh, another 2.6 after that?
That's
And, and technically it goes on past that. It looks like it's probably what? I was thinking it might be repeating, but it's not going to end up repeating. So should be irrational, square root of 9.1. Okay. Leads us to G. Would your linear approximation formula be an accurate tool to estimate square root of 25? Why or why not? Oh, and I guess, by the way, I thought G was going to take us on the square root of 9.1 again. Does this prove that it's an overestimate? Okay. Our answer that is up there. And I believe so the one up above that we have, I have it written down as 3.0166, but technically it's the one from up above, it was 3 1/60th, which is 3.01, and the 6 is repeating. So at that point, it's an overestimate because that is a 6 and it would be bigger than the 2. Okay, so there's the proof. Now, would your linear approximation formula be an accurate tool to estimate the square root of 25? Why or why not?
Yes. Because I don't know if this is right, but so I counted how many, so from the first point to the next point on the line, I counted and it's 9 things to get. Do you understand where I'm going with this?
You guys sound good.
So like after 16, it would take 9 more numbers to get to the next point.
To 25? Okay.
Yes, and we're already at 4, so then it would be at 5.
Okay.
I don't know how to put that into like words, but I say yes because of that.
Let's talk about your linear.
What is our linear approximation formula?
That's I don't remember.
That's our tangent line.
Linear approximation formula is what we did up on part B, C, something like that. That is our tangent line.
All right.
Just have a bunch of numbers.
Okay. Now, so this is saying, would the tangent line we found be an accurate tool for the square root of 25?
No.
No.
No, why not? It's an overestimate. But why is it going to be a bigger I mean, why can I use it for square root of 9.1 but not square root of 25?
Because square root of 25
This
is significantly further along the
Yeah.
x-axis.
And yeah, so when we did, go back to part B. I'm sorry, I wish I could go back on my screens, but I deleted that page. But part B said, write the equation for the linear approximation of f near x equals 9. So we plugged in the ordered pair 9, 3 to get our equation. This would be using the x value 25. We, something around 8.9, 9.1, we're in that ballpark of 9. 25, we're outside the ballpark. Okay? Yeah, by a long shot. We're in the cornfield, okay? Well, nope, our ballpark doesn't face that way, does it? Okay,
You could totally match the cornfield if you get far enough.
there you go.
And softball field. That's
Okay, so square root of 25 is too far away from the point of tangency outside the local neighborhood. No, the square root of 25 is too far away from point of tangency. Outside of local neighborhood. Okay.
1 page down, like 5 to go.
Gotta move. Don't let me get distracted, right? Okay. On the next page. Use the graph of the continuous function y equals g of x, shown below, to complete the table. We know that the derivative of a function at a point represents the slope of the tangent line at that point. we're being asked to estimate the value of g prime of x for each x value in the table by drawing a tangent line through the given point of tangency. Then estimate the slope at that point. Find the y-coordinate of the point of tangency and use the point-slope form of an equation to write the equation of the tangent line at the point x equals a for each x value. Now, right there next it says tangent line approximation of f at a, and it gives you a formula. F of x equals f of a plus f prime of a times x minus a. Realize you know that equation. This is the same as saying y equals y1 plus m times x minus x1.
Oh.
Now, what's the only difference of when we usually write it? Oh, I put y prime instead of y1. My apologies. The way we've been doing it is the y1 is out back. Well, or we have y minus y1 on the left. When we moved it to the right, we've been putting it out after the parentheses. This just has it right out front. And this is the idea that our formula uses the point x1, y1, whereas this formula uses the point a, comma, f of a. Okay? A, comma, f of a is more the calculus notation you might see. Okay, I saw some rulers go out. X equals a, and our a value is -3. So we need to draw the tangent line, yes? So we're going to draw the tangent line here at point A.
Can I get a ruler?
Yep. Well, that's what you get from me. Good enough. You guys understand it's going something like that, yes?
Yeah.
I really struggle. Mine's a little too vertical because it's overlapping with the equation too much, but it's just difficult for me. I'm not saying it's easy for you guys, don't worry.
Are tangent lines on other points of the graph allowed to cross?
What now?
Are tangent lines on other points of the graph allowed to cross?
Like, could it cross another piece of the graph?
Like,
So like B
so
and A.
B and A.
Yes, yeah, they'll be able to, yeah,
Okay.
they'll be able to cross others. Okay, what is our derivative estimate here? Actually, it might be, let's figure out the point of tangency first. What is this point?
Negative
-3,
-3, -3.
-3.
So the point of tangency is just your ordered pair, -3, -3. Derivative estimate.
I have -7/2.
Interesting. Well, mine certainly does not match what I have in my notes.
I just got 7.
Not positive though, right?
No.
Yeah. Mine does not match what I have in my notes.
Everyone's graph. Everyone's graph.
I have -5.
6.
So
-8.
my answer key has -6.
That's nice.
Okay. We're not all going to be the same. These are hard lines to draw. Does my page show -6?
No.
Not the line, because I would have had to go through that point there to make that happen. Which I did say that I felt like my line was a little too steep, didn't I?
Oh, I get how they got -6.
Okay, so like mine should go through there. I'm never going to be able to make this any better though. Nope. I made that worse, didn't I?
Oh, goodness.
And I can't draw a straight line now, so yeah, I don't know. Regardless, I mean, the idea is I still don't have the right angle of the line. Okay. Anyways, you have your slope. As I said, answer key says -6. I heard ballpark answers, right? Okay, so I'll take it.
Yeah.
Now, function behavior at x equals a. Increasing, decreasing, or constant are your choices.
Decrease.
Decrease.
Decreasing. The tangent line is decreasing, so the graph is decreasing at that point. Equation of the tangent line at x equals a. Here's my hint. Y equals.
-3,
Shoot. I'm trying to figure
Negative
this out.
3 minus
8,
Would it be negative
6,
3?
7.
9, whatever.
whatever.
Whatever your slope is.
X plus 3.
I got.
So one option, if we put the y1 first, is put your y value of -3, and then it'd be plus your slope. My slope is, everyone's slope is negative.
Negative.
So minus my slope. So 6 times x
Plus 3.
minus -3, which is plus 3. Now, if you don't like that, then you could also write y equals -6 times the quantity x plus 3 and minus 3. That's equivalent, yes?
Yep.
And yours may or may not say -6 in there, right? That's the only thing that should be different. Okay. We got it. We're good. Moving on. It's -2b, I'm guessing. This one, we should all be able to have the same answers.
0.
0.
Yeah.
Okay.
0.
Derivative estimate is 0, which I'm not even, honestly, do I even need to draw in that tangent line?
No.
I mean, I'll just put a little, I'm not going to draw a big old thing. It's just that, right? So, what is the point of tangency?
-2, -6.
Okay. I was still counting, so I'll agree, though. What is the function behavior at x equals a? Constant. You have a slope of 0 that is constant. Equation of the tangent line.
X equals -6.
No, Y equals -6.
Y equals -6. My bad.
Because it's a horizontal line, so it's going to be y equals. Okay, that was an easier one. Oof, we needed that, right? C.
Your tangent line is going to be on top.
How do you decide if your tangent line's on top or bottom?
Because it won't cross the
Concave.
graph.
Concave.
Down.
Or my tangent line kind of goes through here.
I thought they couldn't.
Yeah.
It can when this is an inflection point.
Oh, that's a vertical line.
Well, no, it's not going to be vertical. My graph would have to be more vertical here for that to happen. Okay. This is going to be, it's going to be the idea.
And it's a secant.
Woof. It's not a secant line if it's just touching it at one point, though. I cannot do this justice. Maybe that's about the best I can do there.
Did yours go through 0, 0?
In my notes, it looks like it does. Well, not quite, but close.
Mm,
To the slope of 4.
I got 3.
I cannot even tell.
I got 4.
I got a negative.
You should not have a negative slope. You can't have a negative slope
You're right. It's not a negative. slope.
because your line is
Just
going
kidding.
up and right or down and left.
I was going.
That is the one thing we have to agree on
I
is
know.
the signs of the slope today. Okay, my answer key says it's a slope of 3. Now, based that on the fact, though, what is my point of tangency?
-0.5. -2.
Which makes that just adds to the confusion there, doesn't it? When
Mm-hmm.
you're trying to then do slope from that point. It is what it is. You get the gist, right?
Yeah.
What's my function behavior?
increasing.
And an equation.
-2 plus either 3
Yeah. I noticed after that first one, I switched it and wrote it the other way. I wasn't writing it her way. So whichever you want to do. So let's see, what did Doug say? -2 plus 3
X plus 1.
x plus 1 half.
0.5, sorry.
If you prefer, you could say y equals 3 times x plus a half minus 2. Now I'm going to repeat colors. Okay, next point, is it D?
Is that another, is that the line?
Yeah, that's what I did.
It is. But wait, does my answer key agree? Yeah. Okay. And that's, you have to be careful. Is it truly the max there? And it is. So derivative estimate is 0. Ordered pair?
I did 1.251.
That's what I was.
Just cause
That's what my answer key has on it, is 1.25 comma 1. Again,
it's definitely not at 1, but
exactly. What kind of function behavior?
constant.
Constant. And regardless, our equation is going to be the same no matter what.
Y equals 1.1.
Y equals 1. Is this E? Nope.
G.
G.
It's G. Everybody.
G.
It is.
See, I can't draw a straight line to save my life there.
4.
Can't draw a straight line, more or less.
4 or 5. What?
It goes 4.
Mine is bigger than that.
Yeah, I was gonna say mine is 2.
Mine should be going through that point right there.
Mine goes like right through 4.
Ooh, best tangent line I've drawn all day.
Hmm.
And I just feel like that's a good tangent line because I feel like I'm truly touching the point
I got 8.
and
Well, -8.
kind of equalish on above and below. I have 7.
I got 6.
It would be positive.
Or positive 8.
It's got, okay, and there again, we go back to, there's one thing we have to have in common on the slope. It is subjective to a point. But,
I'm
okay.
gonna go with
What ordered pair is this?
4, 3,
Yeah, for 3.
What's my function behavior?
increasing.
Y equals
6 times the quantity of x minus 4 plus 3.
What?
Whatever your slope is.
Oh, my slope is 6, yeah.
Mine was 8.
mine is 7.
I got 2.
And again, I'm just sticking with the answer key, so. Okay. You got the gist, right?
Yep.
Yeah.
2 down.
4 to go.
Okay.
Happy mercy.
Investigating slope graphs or F prime graphs. When you plot the motion of an object as velocity versus time. These are referred to as slope functions or F prime graphs. These graphs represent the rate of change of the original function. By analyzing these graphs, you can find where changes are occurring slowly or quickly by observing the rates of change or slopes at the tangent lines at specific moments in time. Okay, consider the function shown. It says that right. Notice the curve at the first point, x equals 1/2. The slope of the curve here appears to be about 1. So on my page, you're looking at the red graph, right? Okay. So notice the curve on the red, the slope here appears to be about 1. Then at x equals 4, which is my blue line, the slope has decreased to be about 1/3. Can you analyze and sketch the slope graph on the grid below? Okay. So, first of all, notice right here. This does not say y. That is f prime. So when we think about ordered pairs here, okay, they referred to this as a slope graph. When we think about ordered pairs, we're thinking in terms of, instead of thinking x comma y, it's x comma f prime. Or I guess I could write that as x comma f prime of x. Okay, those are what our ordered pairs are. So now, if we think about some of these, so at this red one, my x value was 1/2, yes? So on the graph, when x equals 1/2, my slope is approximately 1. On my slope graph, that means I'm going to have a point at the ordered pair 1/2, comma 1. Okay? I know, kind of appears to be in a similar place, but coincidence. Then, what was this? This was when x equals 4. And I don't know, maybe you want to write down, what was that first one we did? 1/2, comma 1, right? So now, it was when x is 4, what's my slope going to be? 1/3. So now, at 4, my point is going to be at 1/3. Because it's the x value, and then this is a slope graph. This is a y prime graph, an f prime graph. Okay, so we did those two. It only gives us some idea of what the graph looks like. You can pick some other points to figure this out. As my x values get bigger, 5, 6, 7, so on and so forth, what's the slope going to do?
Keep going.
It's going to keep going down.
It's going to be getting smaller, yes?
Yes.
Because as these numbers, as my graph goes out, my tangent lines are going to flatten out more, be more and more closer to horizontal, which means as we think about over here, these numbers are going to get
Closer and closer to 0.
smaller and smaller, closer and closer to 0. So as my graph goes out this way, it's going to run along the x-axis.
Yep.
Now, over here, we have a weird thing happening. Because so over here, it's very steep, right? As you get closer to the origin, it's steeper, steeper, steeper. So these values are going to get bigger, bigger, bigger. But then past 0, 0, my graph doesn't exist. Are you seeing where this graph is, what this graph is going to look like?
It's going to be half of the reciprocal function.
Mm-hmm. That's not the best drawing I can do, but the idea there that it's going to keep going, and it's showing how the slope is decreasing there is what I want to say, I guess. Okay. This is a big thing in calculus, and it takes a lot of work to really grasp, but being able to make or read and understand a slope graph, a derivative graph. Okay? Let's look at example 7. Now, graphs will always be labeled, yes? So with this first graph is the regular graph. The second graph is the derivative graph. Okay? So always look for those. The derivative graph gives us the insight into the behavior of the original function. And the hints they gave us, for example, at x equals 1, the slope appears to be almost negative 2. Therefore, in the derivative graph, the value at x equals 1 is almost negative 2. Several relationships between the two graphs that are particularly important to note. Let's explore these features in depth. So, let's see. What did she mention there? The 1. Okay. So right here, when we look at 1, the claim is that the slope is about negative 2 here. So then over here, what is this value at about? At about negative 2. Okay. Okay, let's look at some special cases over here. What about here and here? What do you know about those pieces?
Maxes and mins.
Local maxes and mins.
Okay. Think in terms of slope.
Zero.
They're 0.
Their slope of 0, yes? So if these are slope of 0, at what point is that?
-1.
A little bit above 4 and right around -1. X values.
Oh,
yeah.
Okay. At approximately X values of -1 and around 4, my slopes were 0. Yes? Now, it's a min or a max, as Doug mentioned on the original graph. Yes? What is it over here?
A 0.
They are zeros on this graph.
oh.
Okay? That's important to notice. That, and you can make a list somewhere off to the side, but a min or a max on F is a 0 on F prime. These are important things to look for. Okay. Let's see. Where is it about? Somewhere right in there, right before x equals 2, I'm guesstimating, there's an important feature on the regular graph. What kind of feature is that? Do you know?
The point of inflection.
Inflection point? What's happening there? My graph is changing from
Concave up to concave down.
technically concave down to concave up, if I'm going left to right. But it's changing concavity is the point.
Yeah.
But it's concave down right here, concave up right there. That's a point right before 2. Okay, so it's an inflection point. What do you notice over here at that point?
Oh, it's the.
That's the min.
It's the min over here. Okay, so that's another important piece, is that she usually uses POI for point of inflection. Okay, and in point of inflection on the derivative is going to turn into either a min or a max. And as we learn more about derivatives, and second derivatives, and third derivatives, and so on and so forth, this will all come together, okay? Because point of inflection in my brain talks about second derivative, but we're not there yet.
Do we ever have to watch videos of like the teacher talking or anything?
Not usually, unless I get in a desperate situation. Okay, I did not label this as zeros, but those are zeros, as is that. Should have labeled it in the middle. I'm just trying to look at other things I have. Let's talk about concavity really quick. On what interval is my graph concave down?
Negative
Negative
infinity to
1.5.
1.5.
To something like that.
Yeah.
So concave down. It's concave down the whole first part, yes? So as that graph moves left, that is negative infinity up to, we can call it 1.5. I would say it's closer to 2, but in all honesty, I have 1.5 written in my notes. And then what happens right after that?
Concave.
It's concave up, isn't it? And so it starts being concave up at 1.5 going to infinity.
These are all points.
That's what I have in my notes. I'm trying to think if it could go either way on this one.
Okay. Just the bracket would be on one by that.
So yeah, I don't have a reason why. I'd have to think about that more to rule out brackets totally, but okay. What other connections shall we make? Did we get everything?
For that f prime of x graph, would it just be positive infinity and negative infinity concave?
Concave what?
Uh,
This entire graph is concave up?
Mm-hmm.
Yep. Okay. I think I've gotten all the ones I want to point out. Okay. We'll see more of those. We'll work more with those. Okay. Now,
Is that normal for that style of graph?
what?
Is that normal for that style of graph?
What do
Like the
Like a cubic graph here?
yeah, for the slope to end up being like a parabola.
For the yes.
Okay.
Yes. For a cubic graph, for the derivative to be a parabola is exactly what you would expect.
Will it always be?
And the derivative of a parabola graph would be a straight line. We'll learn more about that later. But yes, there is a connection there.
Is it always like that? Like
Mhm.
anytime? Okay.
Okay, now, if you look at the next page, whoops, went a little fast. When the graph of a function, okay, I forgot there's questions to go with this. Okay, when the graph of a function is rising, we will say that the function increases. And when the graph is falling, we say the graph decreases. It's customary to read a graph in much the same way as we read a book from left to right. You've heard that from me. Not new, is it? Starting at the left of the graph on y equals f of x, state the intervals of x where the graph rises. What do you notice about the slope of the curve on these intervals? So when is my graph rising?
Let's go up.
On f of x or
On f of x.
Oh, those guys.
On right here. I'm looking at this graph right here for the moment.
it rises until negative.
Okay?
Negative infinity to 1. Or negative.
So from infinitely left, negative infinity to
Negative 1.
approximately negative 1.
And then
Where else is it rising?
up 4 to positive.
4 to infinity.
Mm-hmm.
I have 4.2 in my notes. It's something a little past 4. We already knew that, right?
Mm-hmm.
Okay. In both of those cases, what's the slope of the curve going to do on those intervals? But if you look at the slope graph here, before negative 1 and after 4.2, my graph is,
Increasing.
well, positive.
Mhm.
Because so the idea is that when the graph is increasing, the derivative is positive, is what we're supposed to be looking at here. So original graph increasing. My derivative pieces are above the x-axis, which means they are positive derivatives. So I have mine written as, let's see, f of x increases on negative infinity to negative 1 and 4.2 to infinity. Slope of graph is positive. Okay. Now, starting at the left, state the intervals of x where the graph falls. What do you notice about the slope of the curve on these intervals? Well, if we had increasing and increasing,
Negative. No, that's zero.
when does f of x decrease?
Negative 1 and 4. Or negative 1 to 4.
Negative 1 to 4, 4.2, whatever you have.
Mhm.
Yes? Okay. And what's the slope of the graph going to be doing here? Negative.
It's going to be negative.
Slope of graph is negative. If you look, I didn't flip back because I kind of felt like this one kind of followed along. But if you go back and look here, notice in between negative 1 to 4.2, where is my derivative graph? It's below the y-axis, or below the x-axis, so it is negative. At what values of x on the graph of y equals fx does the function appear to have maximum or minimum? What is the slope of the curve at these points?
Negative 1.
We already talked about this, didn't we? That's good. I just have to write it down then. So we already talked about there was I'm going to use the word relative, except I can't spell it. There was a relative max at x equals negative 1. And there was a relative min at x equals 4.2. And both times the slope was what?
0.
Slope of the curve is 0 in both cases, right? I talked about that on the other graph. I even pointed it out, didn't I? Oh, and we already talked about this next one too. Now look carefully at this one. Why does the graph of f prime of x reach a minimum value near x equals 1.5? Can you explain what is occurring at x equals 1.5 on the graph of f of x to create this minimum on the slope graph? Why was this minimum here? There's a point of inflection here. My graph was changing from
Negative to positive.
concave down to concave up. Okay. So I just have written in my notes at x equals 1.5, f of x changes from concave down to concave up. Okay, we're going to practice a little bit of slope sketching. Notice, procedure. Describe how the slope changes from left to right along the curve. Notice the intervals where the slope is positive, negative, or 0. Write down the changes as they occur from left to right on a number line. Notice where x-intercepts occur. Pay attention to where the function is above the x-axis and positive, or below the x-axis and negative. Okay.
It's sketchy.
Okay. With this in mind,
Dang, bro. You got the whole thing.
we are given g of x. Our job is to sketch g prime of x, yes?
Yes.
Okay. So what we need to think about is we need to think about what's happening with g and then g prime. Okay. So we need to think about in terms of slope, yes? As we look at g, what's my slope initially doing? What is my slope doing here?
Going down.
It is a negative slope, yes? My graph is decreasing, if you will. And we're decreasing until what?
-2.
Approximately -2. So I'm going to put a -2 on my number line. And right here, we know that my graph is decreasing. Then what's my graph doing?
Increase.
It's increasing till,
3.1.
my notes have 3.3. Take your pick, but yes. Okay. All I care about is you got the increasing, yes? To me, it's most annoying when we don't have the exact values. But, and then what's your graph doing after 3.3? It is decreasing, yes?
It's like those things we did last week.
Now, as we think about this, that is on terms, I'm trying to figure out best how to do this. That is in terms of g, right? So we're getting ready to graph g prime. A decreasing graph means what kind of slope?
Negative.
Negative. So over here, we're going to think negative, negative, it's going to be a negative. An increasing graph means what kind of slope?
Positive.
We're going to be talking a positive slope. A decreasing graph means what kind of slope?
Negative.
Negative. Are you with me here?
Yes.
I'm trying to be quick, but not too quick.
I think so.
Now, other pieces. What happened at -2? There's a what? A minimum. Whoops. There's a minimum at -2 and a max,
Bless you.
bless you, at 3.3. Okay. Now, what about the slope at those points?
It'll be 0.
Slope is 0, yes? Because those are mins and max, slope is 0. Now, a 0 over on this graph is going to mean it's going to be an x-intercept. Okay.
Point of inflection at 0.75.
Okay. And I'm going to put that,
Point and a half.
okay, I'm going to put that over here. The other thing that's being pointed out is somewhere in here, there is a point of inflection, yes?
Mm,
The answer key says 0.8. 0.75 rounds to be 0.8.
Oh my god.
You know.
I'll do it.
And again, it is what it is, right? So there is what you guys called a point of inflection. Before the point of inflection, what was my graph? It was concave up. When you see me write CU, I'm writing concave up. After my point of inflection, what was my graph?
Concave down.
Concave down. Okay. So
No.
what we need to translate this into. Okay, and we talked about this on the other page. When this graph is concave up, my derivative graph is going to be increasing. When this graph is when my original graph was concave down, my derivative graph is decreasing. Okay. So, we've got some information here, yes? It is hard to think about. It is for me, a calculus teacher, I have to always really keep it together. So what's happening at -2 and 3.3?
Or 0. That's false.
The slope is 0. So these are going to be zeros on my graph, yes? At 0.8, it was a point of inflection on the original graph.
Yeah.
What's my graph doing here?
It's a max.
It's going to change from increasing to decreasing, so it's going to be a max. Now, do we know how high this graph goes?
No.
I would say I don't think we do. Okay, so I need, on this graph, before -2, it was a decreasing graph, which means the slope is negative. Where is a negative slope? Negative on this slope graph is going to be represented as below the x-axis. So over here, we're below the x-axis. Notice, what are we doing all the way up to 0.8? I just put a random point. We're increasing. So the idea here is we are increasing up to this point, increasing all the way up to 0.8. Before -2, my graph is negative. It's below the x-axis. After -2, my graph is,
Decrease.
well, right here, after -2, my graph is
Positive.
positive and above the x-axis. At 0.8, my graph changes from increasing to
Decreasing.
decreasing. And then at 3.3 or whatever, my graph changes from being above the x-axis to below the x-axis. So our cubic, again, became a parabola.
Okay, so then where do you put that?
Yeah, how do you know how high to go up?
How do you know where to?
It was a random height.
Okay.
I did not have, my highest point needed to be above 0.8. I did not have an actual height above that. Is there a way to know? Is there a way to know? Off the top of my head, I don't think so.
That's really bad. That is so bad. Anyway.
Okay. Oh, I guess they gave us directions here. I skipped that. Okay, yeah.
She's too smart for that.
Oh, I just, in my brain, I was like, okay, we got to do this. Mark the number line to show values where it changes from increasing to decreasing. That's what we did. These x values, the slope of the curve is 0. On the function, we refer to those values as extrema or, no, on the original graph, they were maxes or mins. Remember extrema? I introduced that word in pre-calc, so when your pre-calc friends, what's extrema again?
Maximum.
Mins and maxes, okay? Okay, we already did that. Moving on.
We can do it.
We got one page.
Hey.
We're good.
If I can at least get you started on this page, we'll just call it good enough. But okay, one last thing before we go, literally. We've seen that it's possible to estimate the numerical value of a derivative at a single point by finding the slope of the secant line passing through 2 points. Let's explore how this can be done using a table of values for a continuous function. They have to tell you it's continuous for it to be magically working. Use this table to find the derivative for each x value, describe the behavior of the function, explain your reasoning. So, we are being asked to find the derivative estimate when x equals -2. So we're trying to find f prime of -2 when we have this table of values. So we can't see, it's not like we can draw a tangent line and estimate on that. Notice it talked about using the secant line. The secant line is when the line crosses the graph in 2 points on either side. So in order to find -2, we're going to use the points on either side of -2 to find the slope. Because I don't have the information to find, basically, I can't find I rock here. So I have to find A rock. That's essentially what I'm telling you. Now, think slope. Y minus y. I'm going to say -6 minus 4. Right? Over x minus x. -4 minus -1.
-2, -3. So, do you think? Oh my god. I'm so sorry, guys.
10/3.
10/3.
Okay, this is a positive derivative.
Yep.
So my graph is
Increasing.
increasing. And the justification, I'll write on this first one, is at -2, 2. The derivative at -2 is greater than 0. That's how we can justify the increasing. Okay? So now, if we go to -1, what am I doing for -1?
0, -2.
We're using our points at -2 and 0, the two closest points around it. Make sense? So f prime of -1, doesn't matter which way you go about this, 2 minus -1 over -2 minus 0.
Two over -2.
Check again.
Well,
3 halves. 3 over -2.
How about -3 halves, one way or another?
you're struggling. Right. I'm just gonna go ahead and erase.
2
Around.
minus -1
All right.
is 3. -2 minus 0 is -2.
Alrighty.
3 over -2 is -3 halves.
Yep.
Oh my goodness. F prime of -1 is less than 0 here. You getting the idea? One more if I can squeeze it in. F prime of 0. F prime of 0. We're going from -1 to 2. And, is this Hannah's O?
0
I got
over
0.
-3.
4 minus 4 over -1 minus 2. It's 0 over something, which is 0. So we have a constant function behavior. And we know that because f prime of 0 is equal to 0. Okay, throwing in some other magical values for you. 1, -2/3, increasing, constant, greater than 0, less than 0. That's random, I know.
How's that last one constant?
Or it's not constant. And then I wrote less than 0, so don't ask on that one. It is decreasing. Don't ask. Okay, if the derivative is less than 0, then the graph of the function is doing what? It is decreasing. If the derivative is greater than 0, then the graph of the function is
Increasing.
increasing. I almost made it. I got very close. What are these last ones? A relative maximum occurs on a function when the derivative equals 0. That's what both of these last ones are going to be. The difference is if it's a maximum, think about it. Your graph is going up and then down. So your graph is going from increasing to decreasing. Or you can think, I guess I really probably should say positive to negative in terms of slope. This one down here, I'm not going to be able to write it, but it's going to be the reverse, right? If it's a minimum, think about it. Your graph is going down and then up. So it's going to be going from decreasing or negative to increasing or positive. Okay? I kind of did it in a
I think
way.
we were there, honestly.
I mean,
We
some of
made
the
it.
stuff I skipped, I'm like, you guys can fill it. You guys don't need me for that, other than mistakes, right?
Yeah.
Okay, do the homework, see what you can come up with. We'll talk tomorrow.
That's it. I failed it all.
Oof.
Here we go.